right quick before we do get too far into it. Y'all know me. I'm Das. I've got Noah with me. Noah, say hi.
Hello, hello.
There you go. Can you hear us okay? How's the signal? Can you see us? Etc., etc. Before we dive into our next shindig, we want to make sure that everything's good to go here. So give us that 5x5. They're literally our production crew.
That's right.
So they tell us that they can hear us and see us, and we're like, all right, we can start.
Crafting tree. Oh, hi. I'm just reading some of these things. 5x5. Oh, okay, good.
Yeah, what is a crafting tree? Solid. What are you talking about, Saber? Crafting tree. Do you mean like the tech tree in Kerbal Space Program? That's probably. We're looking good. You might need to adjust your monitor if you think.
Yeah, I know what you're saying. I'm glowing. I'm glowing.
It is warm here in New York City today. It's supposed to be warmer tomorrow.
Oh, yeah. It's going to be a fun day tomorrow.
Yeah, but we can go ahead and get going.
Yep.
If y'all can hear us in stuff. You know me, I'm Das. We continue our virtual field trip here at the Intrepid Sea, Air, and Space Museum in New York City. It's coming up on the 50th anniversary of the Apollo landing. And you know, I always say it, it's going to get old at some point. I like to surround myself with people smarter than me. And everybody like rolls their eyes because they're like, that's what he always says. But with me, I have Noah Petro with NASA's LRO.
Yep.
What does LRO stand for?
It's the Lunar Reconnaissance Orbiter. It's a spacecraft that we've had orbiting the moon for 10 years now.
10 years.
The longest lived lunar orbiting mission of all time. You know, Mars rovers always get lots of, they've been going for so long. We were supposed to last 2 years.
Right.
Here we are at 10 years. It's been a real wonderful ride. And
For LRO.
For LRO. And for me, too. I've been building my career along with the mission. Now I help run the mission. I'm the project scientist for it. So it's an incredible honor to be part of that mission, working for NASA. And then, NASA. And here celebrating Apollo.
Apollo.
Yeah.
Good deal. In chat, this is probably one of the more, I call them chat, by the way.
Okay.
That's their name. It's not Chad.
Hi, chat.
Chat. If you want to tell them to do something like chat, check out the LRO website at.
Yes.
You can do that.
Oh, follow the LRO Twitter handle, Twitter feed at LRO_NASA.
Do it, chat.
And my friends run that Twitter account. So tell them that Noah is doing an awesome job. Say hi, Molly.
Everybody watching right now, wait, do a last tweet,
Yeah.
and that'll get the tweet with the selfie of Noah and
That's
me.
right.
And then everybody watching can say that Noah is doing a fantastic job and deserves both a raise and a vacation.
In that order.
In that order.
It's the only way the second's going to happen is we
In
get
that
the first.
order. So then when you're on the vacation, you get the... He's smart, chat.
Absolutely.
So
Anyway.
This is a super serious setup because we're like sitting on a stage and everything. We usually don't do this.
Oh, my.
We walk around the museum or whatever. But we're sitting on the stage. We're in the Intrepid Museum. You're going to be giving a presentation here shortly, right?
I will. I'll be talking about Apollo. I'll be talking about our current exploration of the moon with LRO. And then a little bit of a taste of what we hope to see happen in 2024 with the Artemis program. So covering 50 plus years of NASA history, exploration of the moon, lunar science, and just telling some stories and hopefully having a good time.
Gotcha. The whole thing, huh?
The whole thing in 45 minutes.
In 45 minutes, yeah. How much time do we have? And again, if y'all have questions, I do have my phone. I am reading Twitch chat. There's everybody putting links to LRO NASA and that sort of stuff. There's a link to the tweet so you can make sure you say that Noah's doing a great job.
Fantastic.
Et cetera, et cetera. But if you have questions, hold on to your questions, and then at the end we'll have some time, and I'll read some questions out of chat.
Absolutely.
But if you ask a question when we're in the middle of talking, I might not see it, and it's hard for me to scroll back and find it, so hold on to the questions until we get to the end.
Perfect.
So I got to ask, right? We're talking about Apollo 50th, and it's this huge deal that's coming on because it's 50 years since we both launched the Apollo 11 mission, which was the 16th a couple days ago, and orbited the moon and landed the moon, right? The entire Apollo 11 mission.
Yeah, we started orbiting the moon today, or 50 years ago today. And then tomorrow, the anniversary of landing. And then on the 24th, the return.
The return.
The splashdown in the Pacific Ocean of the Apollo 11 mission, which to me is as important a milestone. It was not only the completion of the mission, but as a geologist, as a scientist, it's when the samples came back.
The samples back.
The 3 crew members, great.
There were astronauts in there too. But
the 48.5 pounds of moon rock is what has made my career really happen. And so, that's the day when the mission ended, but the second half of the mission started and continues on today when we get those samples. And science takes a right turn with the arrival of lunar samples in our labs.
Gotcha. So wait a second, that's something I've heard in the news recently. Aren't they like cracking open some samples that were in storage?
Yeah, so they were very clever at the time. As the missions progressed along, they had more and more advanced sampling techniques.
Right.
And by the last few missions, they were sealing core tubes. So they would puncture down into the upper meter or so of the surface and seal it on the surface of the moon that they would try to capture whatever gases might be trapped there. returned those to the Earth and stored in vacuum sealed. There were some other samples that were collected, brought back, and put into a freezer immediately to basically slow down any weathering that they may have. And so these are what we call the pristine samples. And so several of those have been selected to be opened. And so teams competed, not American Idol style competed, but wrote proposals to NASA.
You get up on a stage, you have to sing about the moon rocks or something?
That's one of the less savory parts of the job that we have, but we do what we have to.
Do what you have to
and
for science, right?
We had now the opportunity to open these samples and understand the moon in as pristine a way as possible. We know bringing samples back disturbs the samples to some degree, but let's try to get as pure an understanding of what the moon is telling us through these samples. And so that's going to be happening in the next few months. And for the next few years, we'll be able to study these samples up close and really, I think, help not only learn about the moon, but also prepare for the next generation of sampling planetary surfaces.
So I didn't know this, there are moon rocks, samples, that came back on the Apollo missions that were never opened.
Right. I mean, there are samples that were brought back that were prepared and analyzed, but have never been analyzed in depth. I mean, I think that, and I forget the number, but easily 50% of the samples have never really been touched.
Never been touched.
I mean, and then there are these very special samples that are kept in this pristine state.
Is that what they're called? Pristine samples?
Yeah, the pristine samples, yeah.
Like sealed up on the moon, and then you bring them back, and you have the moon atmosphere that's trapped in there, whatever was in between the regolith.
We think, we don't know how well the seal is held, but we'll find out.
We'll find out. Yeah. Science. That's how it works.
Science. Yeah.
No kidding. I didn't know that there were some that were sort of sealed up.
No,
like
and actually, there's most of the lunar samples are kept at the Johnson Space Center, and then there's essentially a backup set, some small fraction of that samples collection that's kept in New Mexico in a vault, basically a backup
in a vault
in case
something happens at that physical location.
Exactly.
Gotcha. So I want to sort of tie Apollo into LRO, right?
Sure.
Which is sort of tricky, but when we went to the moon, there were a lot of steps. Earlier on the field trip, we were learning about Mercury and Gemini, sort of the building blocks to the Apollo mission to get us out there to the moon. And then even in Apollo 10, you go and you do a flyby around, but you don't actually land.
Right.
And then 11, you go out there and you land on the moon. But we did other homework on the moon before we actually went to land there. And we had sort of an LRO sort of thing that was out there taking imagery, trying to figure out our landing site. Can you tell us a little bit about what we did? Like, how did orbital operations support the Apollo program?
Sure. Well, so there was a real evolution from really not knowing anything about the moon or how to get to the moon to landing humans on the moon.
Right.
With Apollo 11. We had Ranger, a set of missions to really just hit the moon.
Okay.
Can we launch from the Earth, communicate with a spacecraft, and hit the moon? And what Ranger... Literally, yeah, these are impactors. And I'll show a few images in my talk, that there was a television camera essentially, beaming pictures back every couple fractions of a second as it got closer and closer. And this gave us first the confidence that we could navigate to the moon.
Hit the moon,
but also gave us our first really up-close pictures of the moon. As it got very close, we were able to see features at the scale of what we would expect on a lander. And so it was the first sort of affirmation that, okay, the lunar surface is not it's not completely covered in boulders.
Right.
It's not completely covered in craters, that at the scale of a lander, of the lunar module, we could have smooth spots to land.
A spot that's big enough to target or whatever.
So we did several Ranger missions, and in fact, the first few Rangers failed or missed the moon completely.
Right.
Then we did Surveyor.
Science.
Exactly. Science always wins. Not always, mostly wins.
Mostly wins.
Yeah.
Eventually
yes,
wins.
we'll get there. Time again. Surveyor was a robotic lander mission.
Okay.
And eventually we were landing missions that had scientific instruments on them, cameras, scoops, again, to demonstrate we could land on the moon. We could slow down enough and land. But these were, again, all near side, all proving the mechanisms that, okay, we can get to the lunar surface and we can communicate from the lunar surface.
Near side, like the side of the moon that's pointing to
all
us,
on the near side. And then lastly...
Highly locked, chat.
That's right.
Yeah.
And then eventually we got to Lunar Orbiter. These are orbital missions that map the moon to satisfy our needs to find safe landing sites.
Right.
The first few lunar orbiters were really targeted to finding safe landing sites for Apollo. And really for the first few Apollo missions. Eventually Apollo started feeding itself, where they would scout the next landing site and the next landing site and the next landing site
because
themselves.
We had actually humans there orbiting the moon.
Taking pictures and automatic cameras and all that from an equatorial orbit. So Lunar Orbiter gave us the confidence that we could find landing sites for Apollo, but then also started mapping the rest of the moon. It became a lunar science sort of mission. And what LRO is doing is, we're not landing on the moon, but we're mapping the entire moon not just the equator, but the whole near side, far side, the poles,
The whole thing.
with multiple instruments, 7 instruments, to find those safe, interesting landing sites for future explorers. And so what LRO is doing is trying to do all the things that the lunar orbiters did in the 60s and fill in the gaps in our understanding of the composition of the moon, where there are volatiles and things like that. So LRO had quite the big charge when it was envisioned almost 15 years ago now.
Right.
And now 10 years later, after being in orbit for 10 years, we've mapped the moon, we've found resources, but our science has evolved as well. We're asking new questions. We've identified young volcanics, we've identified volatiles. We see volatiles might be moving around, and so the science questions that we're asking with the same set of instruments has changed. And what my responsibility is to keep the 7 science teams focused on doing their science productive, but then also working with headquarters to make sure we're successful.
Gotcha.
So it's both science, it's a little bit of management, it's a little bit of bureaucracy, but it's a lot of fun, because at the end of the day, we're changing our understanding of the moon, and by its very association, the rest of the solar system, because you can't talk about the solar system without understanding the moon, in my opinion.
Gotcha. I like it. I mean, I don't disagree with you.
Well, thank you.
He's the
That's
expert.
good.
You got to listen to him, right?
Well, can I get that in writing? I don't know.
I mean, Chad, can we put that in writing? So we had these sort of short-term probes, I guess, right? We had Rangers that were impactors, then we had a lander, the surveyors, then we had orbiters, and we went through all these different things, right? And so moving that up to LRO is not an impactor, clearly. Right?
We did fly to the moon with an impactor. We went with the L-Cross mission, which was an impactor. We realized when we had our mission that we had extra mass that we could launch the moon with, so why not use that mass for a spacecraft and not just fly ballast? And so we flew with L-Cross, which impacted into the south pole of the moon in October of 2009.
So you mean when LRO launched, there was extra payload capacity on the ride, on the rocket, and so they built another spacecraft that was an impactor. L-Cross that was?
L-Cross. So what we did was we impacted the empty fuel stage that we launched to the moon with.
Right.
We impacted that, and L-Cross followed behind to see what was kicked up by that impact. They impacted into an area of permanent shadow at the south pole of the moon, area that never receives direct sunlight, literally where the sun don't shine.
Literally where the sun.
And so what they,
I like this. He points at the camera.
Little stagecraft never hurt anybody. But and so they were able to see what was kicked out of this impact crater into the sunlight for the first time, measure water. And then that second spacecraft impacted the moon. All the same time, all the while we're flying over, imaging these events happening as well.
So LRO was already up there.
Yes, we had gotten their moon.
Mission.
Yeah, we had gotten the moon and started orbiting in June, and they were in a long elliptical orbit to eventually be able to come up and impact into the South Pole. So it was this it was an impactor mission along with us.
Right.
And at the same time we've been at the moon, we've seen other missions that have gone to the moon impact as well. So for instance, Grail came several years ago to map the gravity of the moon. They impacted the lunar surface. We observed that impact. LADEE was measuring the atmosphere of the moon, the exosphere of the moon. They impacted as well. So we've kind of recreated some of the missions of the 60s by hook or by crook. U.S. hasn't had landers since 1972, since the Apollo 17 mission.
Wow.
But of course, China landed on the moon earlier this year. China landed on the moon a couple of years ago. So we've been able to see those landers on the surface as well.
Yeah, no kidding. So it's just, I love it, because we talked about, we had these orbiters out there taking images, and then the astronauts would go and orbit the moon and take images to determine the landing sites. And LRO, the work that LRO is doing right now, in part, is going to help us determine landing sites for
the next generation.
Can I say Artemis? Is that a thing? Can I say Artemis?
Yeah, Artemis. Actually, we had today NASA rolled out the logo, so it's got to be official.
It's an official thing.
We got a logo.
Artemis has a logo.
Actually, I want to know who the first person to get an Artemis tattoo.
Artemis tattoo.
Not going to be me. Not going to
be
me.
you.
No.
I got to do the whole taаттoo thing. Maybe like a temporary one.
Yes, I've got tattoo. Yes, exactly. I think a temporary Artemis tattoo would go a long way. But yes, we are charting the places that will become the next Tranquility Base.
Right.
We know that right now the direction is to go to the South Pole, and so we know there are resources there. There are places that receive extended periods of sunlight, and so there is not only scientifically compelling reasons to go there, but there's wonderful exploration resources there as well.
Right. So how do you do that, all right? We talked about volatiles, right? And when we say volatiles, we mean a lot.
Water and ice. But there's other types of volatiles, but those are the big ones that we're interested in.
Because you might think volatiles, that's like fuel, like gasoline, right? Well, no, water is scientifically a type of volatile.
H2O,
right? Yeah. So we're looking for water on the moon because water is fantastic stuff. You crack it out, you got hydrogen in there, you got oxygen in there, you got stuff to breathe, you got rocket fuel, you got water to drink, you have all sorts of stuff that you need for an extended presence. Water, ice is important, and if we can find it, that's good for us, right? So we're talking about finding volatiles. How do you look for them? Like, what does LRO do to try and find where there might be ice?
So we took a multi-pronged approach, water ice. So, as I said, we have 7 instruments, and many of them...
One's like the ice detector, right?
Right.
It's just the ice detector.
It's just looking for ice.
Looking for ice.
Is there ice there? Is there ice there? Is there?
Rocket science.
Right, actually, honestly, right now I could use a little bit of ice.
Really?
I could use some of that moon ice right about
like
now.
a fan or something.
But basically, the way we picked those instruments is we put out a call to the science community. What do you think we need to? How do we want to do this? And basically, what happens is everybody takes their favorite instrument and says, "Oh, you need this one."
Right.
So we look.
This.
I got this. Yeah. So we look for we have an ultraviolet mapper.
Okay.
Similar to something that flew by Pluto. A lot of these instruments were ones that had flown before or had similar. We have a neutron detector contributed by the Russians that measures neutrons. Neutrons are released in hydrogen, and so we're mapping hydrogen with that and assuming that there's water there. We have a radar instrument that's looking for the radar signature of ice.
It has a radar signature?
Yeah, so imagine a radar beam coming in, interacting with the lunar surface. And then we know if it's rock, it should reflect in a certain way. But if there's ice, it will attenuate that signal in a different way. And so we look for a very specific signal for ice in the radar waves.
Okay, gotcha, thank you.
We have
It's like all 7 instruments go.
Exactly. We have an altimeter, a laser instrument that's pulsing the lunar surface. But because it's an active instrument, a laser beam pulsing down to the surface hundreds of times every second, we can also map the moon in this active mode. So whether the sun's out or not, we are illuminating the surface with a laser beam. If you have a red laser pointer or green laser pointer, it shines. We're shining the lunar surface with that laser beam.
Right.
And then measuring the returned energy. Well, we can create a map of the moon at that wavelength range and look for areas that might have frost, might be brighter than the surrounding areas.
Because the laser would bounce back differently,
right.
Like it would reflect more light or different light.
Exactly.
No kidding.
So we've been able to create a map of the moon that shows what the surface of the moon looks like at 1064 nanometers. And we indeed see areas in the south pole of the moon that appear brighter than we might expect.
No kidding.
We have... I'm going through the list of my instruments
right
now. We have a high-resolution camera that is imaging the standing. So exactly, visible. So it's showing us what the surface actually looks like, so we can identify hazards. We have a radiation instrument that actually, in new modes of operation, is sensitive. We found is sensitive to hydrogen.
Right.
And so we're mapping hydrogen in the upper 10 centimeters of the surface. So let me back up for a second. We map all of these instruments are sensitive to different depths.
Yeah.
The imager, you're looking at the surface.
Okay.
The laser altimeter, you're looking at the surface. The radar instrument is actually probing the upper several centimeters of the surface, tens of centimeters. Exactly.
Okay.
The neutron mapper is mapping neutrons in the upper meter of the surface.
So
we're getting essentially a 3-dimensional view of the moon. But because we've been there for now 10 years, we're seeing changes on the surface of the moon. So we're actually mapping the moon in 4 dimensions. So we're really the first 4-dimensional mapping mission at the moon ever.
Gotcha.
Before us, the longest-lived mission at the moon.
Fourth dimension is
the
time.
fourth dimension is
time.
time. Yeah, it is.
It's
time.
Explaining the 4th dimension. The longest mission before was
like 2 years.
Yeah.
Because before us, it was okay. We've mapped the moon. That's it. And now it's not enough just to have mapped the moon, but now it's to look for changes. But then also, when we find something interesting, well, let's look at it in different ways. Let's wait when the sun is low or high. Let's look at it at an angle. So we really throw everything we can at any of the anomalies that we find, any of the interesting areas, to really kind of get a comprehensive view of what's going on in the moon.
And it sounded like one of the instruments, maybe surprised you isn't the right way to say it, but you said you found it reacts to hydrogen or something. It's sensitive to hydrogen, I think you said.
So you
sent it out there not knowing it would do that specifically, and then you noticed something like, oh, we can use that.
So this is an instrument called Crater, which was actually sent to map the radiation environment.
There's a crater.
Yeah. Unfortunately, if you wanted to Google for the instrument, Googling like NASA moon crater, not very useful. So that's a bit of but it's a...
Try NASA LRO instrument crater.
Right.
Then narrow it down.
So it's the cosmic ray something or other. That's a lot of letters.
Ray something or other.
But it measures radiation, and it was sent to basically find out what the radiation environment at the moon was like, so that when we send humans there, we know what's going to happen to them.
Right.
And as they mapped the moon and repeatedly, they noticed that their signal was changing, and especially if they looked at the surface, not straight down, but off at an angle, that signal was attenuated. They actually did some experiments at Mass General Hospital in Boston using a radiation machine there. Okay. Radiating lunar simulant, and then adding water and looking what changed. And so there was an experiment. Oh my goodness, this is telling us. And so they have basically validated that they can make observations that can detect water in the upper tens of centimeters of the lunar regolith. But then by doing it repeatedly over several years, we can watch that signal change as the amount of volatiles in the surface moves around.
The map of where water might be changes a little bit, and you can see the effect of time on the water deposits. I don't know if deposits are right.
Yeah, and so now our view before 10 years ago was that the moon was bone dry.
Right.
The analysis of the Apollo samples, and this is what was so important about getting the samples back, was that there's no water in these samples. They're bone dry. And so for decades, it was thought that any water that was measured was either contamination from the Earth's environment. On a day like today, it's not surprising if anything exposed to the Earth's atmosphere, it's going to get hydrogen, it's going to get water on it. Exactly.
Honestly,
and so 10 years ago or so, there was the first detection measurement of lunar samples that had water in them. And you'll see in the video, the talk I give, I show the moment that sample was collected, but it was determined that inside those samples there was water. So at first we found that there was water in the moon.
Right.
And then we found water on the moon through instruments on LRO, as well as instruments that were on an Indian mission. And so this was the first definitive measurement of water on the moon, in the moon. And then with L-Cross, we saw that there was water below the surface, in the upper 10 meters or so of the surface. And so all of a sudden we went from having a bone-dry moon to a literally bone dry, because of course human bone has water in it. So there you go. So we were right, but for the wrong reasons. Or wrong for the right reasons. I don't know.
Right reasons. Technically correct.
Yeah, exactly.
The best kind of correct.
So that revolution in our understanding of water on the moon has really come about in the last 10 years, in part because of LRO.
Right, and that's a reason that there's a renewed interest. I guess,
exactly. There's this resource, and
it's not just a totally boring, empty place.
No,
and water there.
And even if there was no water there, it wouldn't be totally empty and boring.
Sorry,
it's a little more.
You insult the moon.
That's right. Yeah, come on, moon. It's okay.
It's okay.
But the other interesting thing is, before LRO went to the moon, we thought that these areas near the South Pole that are very cold and permanent shadow, that's where the water would be found.
Right.
It makes sense. It's cold. It doesn't get warmed up. But now the view is that there are some places in permanent shadow that have water and some that don't.
Okay.
And there are places that are illuminated that have water and obviously some that don't. So It's a very different dynamic environment than we predicted.
Okay.
At the same time, we had a mission at Mercury, a messenger mission, and it found essentially a 1-to-1 correlation. If there's permanent shadow on Mercury, there's water there.
Really?
Yeah, and we don't see that at the moon, and so that's a really compelling question. Why is the moon and Mercury so different?
Yeah.
They should they be the same or not? We don't know.
So the sun.
But then you have these permanently shadowed craters. I mean, the sun, hot, don't mind proximity. So it's going to be really hot close to the sun, but it's still going to get warm enough on the moon to boil off the water. But there's water that's still seen there, and so we know water's. So anyway, all of these questions beg us to ask what's happening with the volatiles at the moon. We could use another mission to orbit the moon to do this, and then, of course, going and actually putting our hands on
ground truth.
Exactly. That's what we're always after.
Equipment on the ground that actually scoops up something and says, yep, that's
this
water.
Is what it is. Well, and how much water is it?
Yep.
How much, in what form is it? And then there's a science question.
Enough to worry about.
Yeah, is it water from comets? Is it water from asteroids? Is it water from the Earth? Is it water left over from lunar formation? What is it? We don't know. No.
Right? That's like an unsolved mystery about the moon, because we don't know. We went to the moon in the 60s and 70s.
I think I saw that episode of Unsolved Mysteries as a kid. Robert Stack, 1866. I forget. There was a phone number to call.
What you're talking about, yeah. Oh. Call for information or whatever. Yeah, I know what you're talking about.
Have you seen Sasquatch? I'm sorry.
On the moon.
Yeah.
No less. So we have probably about 10 minutes.
Okay.
And I wanted to roll something back to Apollo.
Yep.
Right?
Yep.
And I mentioned this to you to make sure we were cool with it. We have all these sensitive equipment on LRO.
Yeah.
And one of those is a visual imaging equipment.
Right.
Right? And we also have people on the internet. They're like, we didn't go to the moon. It's all fake. They did it in a sound studio. Never mind that it would have been easier for us to go to the moon than it would have been for us to fake it with the technology at the time. Whatever, right? We've got this guy here who's with the LRO, the Lunar Reconnaissance Orbiter.
Yep.
What can the Lunar Reconnaissance Orbiter see that proves we're on the moon?
So I remember very early on in the mission, we got to orbiting the moon in June, and by early July of 2009, we had our first images of the Apollo landing sites. And we were in an orbit that took us high above the Apollo landing site. So we got to see that, okay, there's the descent stage.
Right.
We can see the bottom half of the lunar modules at each of the 6 Apollo landing sites.
So where you expected them to be?
Yeah.
Okay.
We saw, and compared to what we saw in the images, exactly where we wanted them to be. And as the orbit got lower, the quality got better. We could see higher resolution things. So we could see, for instance, at the Apollo's 15, 16, 17 landing sites, we could see the rovers.
Yeah, the rovers.
We could see the experiments that were set up at all of the landing sites.
Right.
We could see the boot prints around the lunar module at all of the Apollo landing sites. We could retrace exactly where they went. We could see at Apollo 12 where they went and sampled Surveyor 3.
Right.
And for me, most excitedly, we could see the backpacks the astronauts wore and left on the surface.
They left on the surface,
and those are things my dad built.
Yeah.
So for me, that was a very physical, like, that's my dad's work.
My dad's,
look at that.
I love that backpack.
We also could see at the Apollo 12 through 17 landing sites the flags. We can see the shadow of the American, or the shadow of the flags that was left behind.
So when the sun's at a certain angle.
So you see a bright shadow, and it moves around like a sundial.
Right.
We can't see any color in these pictures. We can't see if there's any stripes.
But these are visible pictures, right?
Yes, it's what you actually see. It's right there. And so we know the flags are still flying. I assume that they've been bleached, and so that they're just they're white as sheet white. Yeah. But for off-the-shelf nylon flags, it's remarkable that after 50 years, they're essentially still standing in a pristine state. So we could see all of the traces of Apollo.
Right.
In the same way, when you fly over, sites in ancient Egypt, you can see the ancient streets. Well, we could see where the astronauts lived and worked for 3 days there on the moon, or we could see where they deposited their equipment. And so for me, that was not only gratifying, but it really kind of helped, I think, bring Apollo into the 21st century.
Sure.
Now, of course, we've got all these amazing images they took, and we've got the movie that's come out. And so all of this really restored documentation of the missions. And I think LRO plays a small role in that because it gives it the context.
Yeah, absolutely.
We never were able to see in orbital images exactly the kind of quality we can see now. You can actually, in some of the Apollo 15, 16, 17 images, you could see the bottom. You could see the shadow of the lunar module in some of the images. Very, just a pixel. It's right there.
What is that? Sasquatch on the moon?
Exactly. Yeah. But now you can see definitively the landing gear on the lunar module. You can see the experiments. So
the shadows of the flags.
Exactly.
The
all of this stuff just there, sitting as it was touched when the crew left. Less than 50 years ago now, but 50 years ago.
So that's awesome because we talk about LRO or missions, these long-range probes, as they're scientific. They're going out there and they're gathering the scientific information. They're flying by Pluto. They're going to Mars, whatever. But LRO is almost unique because it's also historical.
Yes.
It's gathering human historical data from our visits to the moon.
Yes, and we see where the Surveyor landers are. We see where those impact craters caused by the Ranger missions are. So we see the traces of all that buildup to Apollo archived on the lunar surface, and we know exactly where they are now, with the precision of if it's near the Apollo landing site, several centimeters, or even further away, meters or so from where we think they might actually be. So it's I had never thought of it that way. It's a really good way of thinking it because for me, it's always been not always been about the history, but part of the excitement is that history.
Yeah, absolutely.
And now we've archived that history in ways that I don't think we ever thought we could. And you'll see in my talk that I highlight almost all of the Apollo landing sites. One, because we have this history, but because we have the samples from there as well. Those samples, our data, we have context for where they were collected.
That makes sense.
And it helps tell the story of the samples and really let us ask new questions about those samples that we never were able to do before.
Gotcha. So you said your presentation. I mean, the screen behind us, we're not done with NOAA here. You have about...
Oh, man, I'm sorry, guys. Yeah,
like a 45-minute, an hour-long presentation?
Well, we'll see.
We'll see.
It's supposed to be 45 minutes. I tend to run long. I tend to go long, but and lots of videos because I like to take a break periodically and let the pictures do the talking for me. But I'm always been a fan of Apollo, and so to be able to celebrate the 50th anniversary of Apollo 11, celebrate the accomplishments of LRO as we celebrate 10 years at the moon, and also look forward, for me, is a very satisfying thing. I mean, I've been passionate about the moon for my entire professional career as a kid. And now to have it as my job, as my responsibility to educate, inform, and communicate what we're doing is a real joy.
Well, we appreciate you. You've done a fantastic job of educating and informing us on the.
I hope so.
Tweet. Remember that tweet, y'all? Where you're supposed to say what a good job he does.
And I also want to. We should take a moment to reflect that 50 years ago, we all did something really remarkable. Yeah, I wasn't there, but it was a global accomplishment. I know that hearing the astronauts talk about on their world tour, they didn't hear people say, well, you did this. They said, we did it. Humanity did something very impressive. And I think maybe now is a great time to try to remember that event and hopefully get on the road back to that kind of global coming together.
I appreciate it.
And speaking of come together, as a Beatles fan, so the same day that Buzz Aldrin and Neil Armstrong set foot on the moon and walked on the moon, it was July 21st in London, in England, 1969. It's the same day the Beatles started recording Come Together.
Really?
Take one of Come Together was recorded the same day that the astronauts walked on the moon.
Inspired by the moon.
I don't.
Maybe, I don't know. Like,
I'd like to think so. I somehow
I'm not a historian.
doubt it,
I can say stuff like that.
Exactly.
Like,
Exactly.
So I think we have just a minute or two, right? We have just a minute or two. I got a question for you real quick, but chat, y'all be putting some questions into here, and I'll read them and pass them on to Noah here. We have just a couple minutes. You said LRO's been up there for 10 years.
That's correct.
I'm starting. I get to go first because I'm in charge.
That's right.
LRO's been going for 10 years. Did you start with LRO? Have you been with it the entire time?
So when I started, when I got to Goddard Space Flight Center in Greenbelt, Maryland, I got there in 2007. LRO was being built, so I got to see it built. It was launched in 2009. In 2009, I was hired on as a civil servant, and so, I mean, I've been associated with the mission my entire career.
Gotcha.
Started out basically supporting their communications, talking about the moon, talking about the geology of the moon, then brought on in the project science office, supporting the mission, and then making my way up as an associate deputy, and now I'm the project scientist. I'm the Le Grand Fromage. Yeah. Project scientist, which I remember telling a friend of mine a couple of years ago. Project scientist. That sounds like something like in high school you have to do for homework. Okay, thanks, Miles. So anyway, but it's a great joy because it's an exciting mission. It's an incredible amount of responsibility, but with great responsibility comes great power.
I think that's how it goes.
Something like that.
But
but there's no power because it's all about the science. I let the science do the work and I follow.
Sure. And support it and share it with us.
Yeah, exactly.
Which is absolutely fantastic.
And hopefully get young people excited and into lunar science.
Because you literally grew your career around, because you sort of started off and here you are now.
And actually that's the real other great part about having a 10-year-long mission is that we've been able to train multiple eras of students.
Right.
You know, I came on as a postdoc very early in my career. Now I'm a little bit more senior in my career, but there are other people who are just out of graduate school, just into PhDs, who are working on the mission. So we're really cultivating a whole generation of scientists who will help lead us back to the moon and continue pushing lunar science along.
That's fantastic. It's like an actual laboratory orbiting the moon right now.
Exactly. Yeah.
You use it to get the next generation up?
Yep.
No kidding. Let me see if there's any questions here. The Lola instrument measures elevation on the moon.
Yep.
All right, Wikipedia. Have there been any surprising formations discovered by this instrument that weren't expected? Like, is there an arch or something? Is there a statue of Neil Armstrong somewhere?
Not yet. Not yet. Eventually, Tranquility Base will have a statue of Neil Armstrong. So Lola's big surprise was, I'd say, well, in that they've been able to measure not only topography very, very precisely, but also the reflectance of the moon, finding these bright areas near the South Pole that appear to be associated with frost.
Right.
You know, the issue with Lola and finding small features is that, you know, the footprint of their signal is fairly large, so we can't see very, very small features. I'd say the surprises that we've seen from LRO have come from the camera.
Okay.
The high-resolution camera, where we've been able... Visible camera. Where we've been able to see pits, voids, caves on the moon. We've been able to see these skylights that expose areas that might be extensive lava tubes beneath the surface. That was a surprise. We've identified areas that may have very young volcanic features, as young as 30 million years old.
Which is really young.
Really young for the moon. Right.
Yeah,
Before LRO, we thought volcanism ended on the moon about 1 billion years ago. So to see it now extend back to recent geologic history is very surprising. So I'd say that many of the small-scale surprises on the moon have come from the camera. The other interesting thing that the topography that Lola has been able to do is when imagine LRO's orbiting the moon and we're laying yarn out beneath our path.
Right.
And so every track goes over a slightly different spot, but every once in a while our orbit, it shifts and we get a crossover where one track crosses over a previous track. And so we know exactly where the spacecraft is. We have confidence we know what the altimetry is telling us. We actually have been able to measure the tide of the moon. The moon's squishing a few centimeters as it goes around the Earth. And so we've been able to measure with Lola the tide of the moon.
Like the physical structure of the moon?
Physical being squeezed. We think of the tides of water on the Earth, the oceans. There's a solid body tide on the Earth as well, where the rocks are actually being gently flexed as well.
Wow.
And we can measure that with Lola on the moon. And that's the first time we've directly been able to measure it from orbit.
No kidding.
Which is a really remarkable accomplishment.
That's crazy.
But true.
But true. Let me see here. Let me see. Did LRO image some of the Russian impact sites?
Sure.
Soviet impact sites?
So we've imaged all of the anthropogenic.
If it's on the moon.
We've imaged it. certainly was a target. We found both Lunokhod long-distance rovers, the Luna sample return missions, the failed Luna 23 mission,
right,
which was supposed to return samples from Mare Crisium. It actually tipped over after landing and never was able to return. We were able to image it and determine that it had tipped over for the first time.
So you could see that it was tipped over?
Yes, you could actually see the hardware landing on its side, and we can compare, it's a fuzzy image, but you compare it to what we know it looked like and say, okay, here's the sample return capsule, here's the descent stage. We could do that. We were able to precisely locate the Lunokhod 2 rover, which had a retroreflector on it. For years, they've been trying to laze to it. So we have these mirrors that the Apollo astronauts left behind.
Right.
There was one on Lunokhod 1 and one on Lunokhod 2, and we sort of lost where Lunokhod 2 was. LRO was able to find where it was, and now we have essentially a new mirror platform on the surface to range to.
Reflect off of.
Yeah, so that was a real great accomplishment. And again, by imaging these anthropogenic, these human artifacts on the lunar surface, allows us to tell that story.
Yeah, anthropogenic is we made it. Basically.
Oh, right, yeah.
We're the genesis of it. No, that's fine.
Yep.
I'm a translator. Like, that's my job is to sit here and do that. I think we are probably about 10 minutes away from your actual presentation here. It's 7:30, right?
I am at 7:30.
Yeah,
right.
7:30. So we're going to have to go ahead and shut this down so we can make sure you're well prepared for that. But Chad, we are going to share the entire presentation with Noah here. So talking about the videos, talking about all the imagery you're going to share with us, that's coming up next in about 10 minutes. Noah, thank you so much for the time.
It's my pleasure. Thanks for having me on, and thanks, chat, for participating. I don't know if we'll have an opportunity later on for questions, but certainly if you get questions, I can feed them to you, and you can get them out to the chat.
Yeah, absolutely. And when I think if we take some questions from the crowd, if the crowd's sort of slacking off or something, I might get some from the internet.
Perfect. That'd be great.
So if you had a question you didn't get a chance to go now, or you watched the presentation and it jogs your mind, you think of something else, feel free to ask, right? So y'all know the last thing. Tell Noah thanks in chat. Put some hearts over there. No, I'm not kidding. Let's start putting hearts in.
Oh, wow.
They're pretty well trained, actually.
Thank you, Saber in Space.
Yeah, see? Look at that.
Thank you.
Jeez. There you go. See, now there's the delay.
All right, man. That's Pluto. Mad Humph. Thank you, Mad Humph.
Yeah, little hearts.
Defiant Zombie.
Fantastic. Absolutely. Thank you so much for the time, Noah.
My pleasure. Anytime.
Appreciate you.
Thank you.
Good deal. Chat, what we're going to do, we're going to go to the Be Right Back screen real quick. When we come back, it'll be Noah with his presentation. Again, we're at this Intrepid, where are we again? We're at the Intrepid Sea, Air, and Space Museum, celebrating the 50th anniversary of Apollo 11. Give us about 10 minutes, and we'll start this.
Is that a hot dog? Oh, no, that's a shining heart. Love. I think that's a frog.
I think it does look like a frog.
Purple heart.
There might be a Kerbal, actually, in there.
Oh, okay, there you go,
We got some Kerbals, yeah.
Fantastic.
It looks like toast with hearts
One
on
love. Ooh, I could use some toast right now. I'm pretty hungry.
Toast and
Won't lie, I'm pretty hungry.
Chat, we appreciate you. We'll be back. Hang in there for us. There's a really awkward count where we have to go to like 7, like 6, 5, 4. No, and then there's a delay, and if I hit it too soon, it cuts off.